after we've seen what the expectation is, the next related quantity is the variance. While the expectation measures sort of the average value, so what is would be the most typical outcome of a certain random variable, the variance measures by how far the actual realizations of this random variable deviate from this expected value. And in machine learning, in particular in machine learning theory, but also in other fields, we often, a good situation is if the variance is very small, because then we can measure the expected value and know that the actual value, the one that we might want to, or that we would observe, is very close to the expected value. So we need to have tools to measure this deviation of random variables from their expectation. The simplest such tool is the variance, and later in the lecture we are also going to see more elaborate concepts like concentration inequalities, but that comes much later. So let us now introduce what is the variance of a random variable. And as before, we do it in the discrete case first. Maybe I take this down here as well. Discrete case. And as I said, the continuous case is coming later. So consider the following definition. We have two random variables. They go from any kind of standard probability space omega AP to R. Again, we are in the setting where we have values in R. And assume these are discrete random variables. And now we need to make another assumption with the expectation of x square is smaller infinity, and also the expectation of y square is smaller than infinity. We are going to need that because otherwise we cannot compute the variance. We are going to see it in a minute. And sorry, here's a parenthesis wrong. Okay, so now we have we consider the variance of x, which is the expected value of x minus e of x squared. And this guy is called the variance of x. Okay, so maybe let's look at this for a second. So we look at the random variable x and how far it deviates from its expectation. Maybe I also make a figure to explain it. So consider we have this red random variable and we have this blue random variable. Now the blue one maybe has its expectation here. These are now, the plots of course are not always so symmetric. Okay, so these are two random variables, a red one and a blue one. Now what does the variance measure? The variance says, we look at the expectation of x, we're now in the red curve, that's here, and any other point x. So say we pick at this point x here. And now we want to sort of, what is the expected value? How far is x away from this center point? Now we have different types of points here. So maybe here, some out here, there are very, very few points. So even though here might occur a point x that is very far and would drive up the expectation of this expression, it has such a low probability that it doesn't really count a lot. Whereas here, there are lots of values around e of x. They have a quite high probability as indicated by the density, and their deviations would add up to something, but maybe not something so substantial because the distance here between x and e of x is very small. So this red curve would maybe have a moderate variance. The blue curve on the other side, so the deviations are much larger. So the expected value of this deviation, this is what the variance is about, would be much higher. So maybe I write just this has a high variance, and the red guy has a moderate variance. Well, whatever high and moderate now means, but that's the intuition we should have. Okay. And so this is the variance of a random variable. Okay. Now there's also the related concept of standard deviation, which is just essentially the thing without the square. So this guy is called the variance, and we have this other guy, the square root of the variance of x. Sometimes this is denoted as sigma x, is called the standard deviation. Is called the standard deviation. Okay, let's also make it yellow. Okay. These are the two notions. If we have just one variable, how does it deviate from its expectation? And then there is another thing that is the covariance. That's if we have two random variables. And I write it down first. The covariance of xy is defined as the expected value of x minus e of x times y minus e of y. Let me count the parentheses, I think one more. So this is called the covariance of x and y. Okay, and I'm in a few minutes I'm going to give you much more intuition on what this covariance is about. So the intuition is that it measures whether the random variables x and y behave very similar in a certain linear way. But let me explain it in a minute. I just want to finish this definition first. Namely, there is one more notion that I want to introduce. Namely, this covariance can be any number essentially, and sometimes we want to normalize the number to be between -1 and 1, and then we talk about the correlation coefficient. And I want to write this down first. So rho xy is the covariance of xy divided by the standard deviation of x times the standard deviation of y. And this is called, as this is maybe, first of all, it's a number in -1, 1. And this is called the correlation coefficient. Sorry. Correlation coefficient. What else did I want to write in my definition here? One more thing, if this correlation coefficient is 0 or the covariance is 0, the two random variables are called uncorrelated. If the covariance between x and y is 0, then x and y are called uncorrelated. Okay, now one more last thing, and then I'm going to give you the intuition. Now, what we've seen so far is we looked at the expected value, which was essentially sort of we sum up the terms of the standard, like the results of the random variable itself. Then we have the variance, which sort of has a square here. And of course, you can also have higher powers than 2. In principle, you can look at the powers of order k. And this is then what is called the kth moment of a random variable. So more generally, for k in n, we define the terms, and I just write them down. E of x to the power of k. This is called the kth moment. And you can, of course, also look at the centered version, x minus e of x to the power of k, which is, or maybe I write it in the next line, e of x minus e of x to the power of k, which is the kth centered moment. Okay, so these were lots of definition. Case moment, case-centered moment. The moments are important. So essentially the expectation is the first moment, the variance is the second moment, and then you can compute more and more moments of random variables. Now the moments are really important because, like, intuitively, what does an expectation do? It tries to characterize a random variable by one number, the average value. And there are certain random variables for which this one number already tells a lot. So for a normal, for a normal distribution, as we see it here, I mean, this is supposed to be a normal distribution. This expectation, once you know the expectation, you already know a lot. Because the random variable is not something completely crazy. I mean, you could also have a random variable, I mean, just for the fun of it, that has a density that looks like this. And then maybe the expected value would be here in the middle. Then this expectation of x wouldn't really tell you a lot about your random variable, because this is not a typical value at all. It's the average, but half of your population is much lower and half of your population is much higher, so it doesn't really tell you so much. For a normal distribution, like here in this plot, the average value essentially tells you nearly everything already. You know it is a mode and so on. Now, characterizing a distribution with just one number may be a bit too ambitious. Maybe you need more numbers. So the next moment you use is the variance. The variance, in case of a normal distribution, if you know the expected value and the variance, you know everything about your distribution. So it's completely characterized in this way. But now if you have a distribution that is more complicated, like the one I've plotted here, probably even if you know the variance and the deviation, it doesn't tell you everything. But maybe what now happens if you include more and higher order moments. And so this is sort of the problem of moments in probability theory, under which conditions, like if you would know in principle all the moments of a random variable, under which condition could you reconstruct the random variable? Like intuitively, it's a bit like a Taylor decomposition. Like in analysis, in calculus, you have a complicated function and you wouldn't want to say, well, I want to characterize these complicated functions just by much simpler terms, by a linear term and a quadratic term and so on. And hopefully it works. And here you have the same intuition. You look at the first, like the linear term, the expectation, the quadratic term, the variance and so on, and you increase higher and higher powers. And hopefully you can characterize the probability distribution in this way. This is why moments and even higher order moments are really important. But for machine learning, in most applications you will ever encounter, the first two moments are the ones that are interesting. And what I now want to convey to you, because this is also in data analysis, it's one of the key concepts, is to understand what a covariance is and what a covariance is not. This is really important. I want to give you a bit of intuition for covariance. Intuition about covariance. So let's look again at the definition. Maybe I write it down once more so we have it here and I don't need to scroll all the time. Sorry, the covariance of two random variables x and y is the expected value of x minus e of x times y minus e of y. Okay. Now, when is this covariance high? I mean, first of all, maybe observe these numbers can be positive or negative, right? So depending on whether your actual value is currently below or above the expected value. But now let's assume for a moment we have two positive numbers. So when is this number or this product high? It is high if both of the components are high. So if one of the components is close to zero, then the other component being high, then this expectation maybe doesn't get so high. This expectation really gets high, or the covariance gets high, if you have the property that high numbers of x also indicate high numbers of y. And if you try to plot, and I want to give you a couple of examples. So let's look at an example here. You have the population of Germany, x is the shoe size, and y is the height of the body height of the person. And maybe how does it look like? Now you sample people and you always, for each person, you put a dot in this, the measurement. So this is for one person, shoe size and body height. And you do this very often. And you might find something like that. So typically people who are tall also have large shoe sizes. people who are small have small shoe sizes. And this is the typical scenario where you would have a positive large covariance. So intuitively what happens here is the covariance characterizes linear kind of relationships between random variables. Here we have a very nice linear relationship. We can predict, so like intuitively what you always want to say is the covariance is high. This means they are very dependent. So once I know, for example, the shoe size, I can already pretty accurately predict what is going to be the body height. And in this example, it's going to work. And what I want to show you later on and try to convey is the covariance is high if you have such a linear relationship. There might be other relationships where you have lots of dependency, but the covariance is low. But this is sort of the case you would have in mind. There's a linear dependence, at least in tendency, between the two random variables. The slope is increasing, then the covariance is high. And how does that happen? I mean, again, look at the formula. So here we have these values where the shoe size is really high and the body height is really high. So we have these products being very high altogether. And similarly, now observe, I mean, I plotted the random variables not in a centered way. But what you do here is you center them, which means essentially you introduce a coordinate system that sits maybe like this. Because you shift your points by such that the expectation, like this new random variable is the centered random variable that has expectation 0, and here as well. And now here you have again these values x is high and y is high, and at the other end you have the same. So if x is very small, like very negative, the absolute value is high but it's negative, then the same is true for the shoe size, for the body height. And then again, this product is going to be large because both are in absolute value high and they have the same sign, so it ends up as a large number. So this is the typical situation where the covariance is high. Another situation where you also have a strong covariance is a situation that might look like this. So you have the price of an object, so this is sort of economics. You have price and you have demand. So if the price is really low, then many people buy this stuff, and the higher the price gets, the less people want to buy it. Say, I don't know, a book or whatever. And sort of this is, I mean, I don't know whether the people in economics would really say there's a linear relationship, but at least there would be a sort of a linear trend. If the price gets higher of the same object, then the demand might decrease. And what do we have here is we have a negative covariance, but large in absolute value. Large in absolute values. And now the point is the absolute value of a covariance doesn't tell you so much. So this is why we often talk about the correlation coefficient. So here we might have a correlation coefficient which is maybe, I don't know, I mean, I'm completely guessing, of course, maybe it's 0.9. And here the correlation coefficient rho is going to be minus 0.9, something like that. So the correlation coefficient is always between -1 and 1. The extreme sides are +1 and -1. That's when you have a perfectly linear relationship. So if x and y are identical, for example. Okay. Now I want to show you some more figures. And this is what I really want you to have in mind. You could also have a random variable that is distributed like that. So you have x, you have y. These are sort of abstract things. We sample lots of objects and always measure x and y. And it looks like this. Of course, now these random variables are dependent because if you know something about x, so for example, if you know x has this kind of value, you pretty much can conclude what is y. So there is a dependency between x and y. And a high dependency. So from x, you essentially can conclude y. So there's a lot of dependency. However, these random variables are uncorrelated. So the covariance here is about 0. So uncorrelated. Correlated. So you can have, and the problem here is that this sort of, if we look again at this expression here that defines this covariance, there are lots of terms that cancel here because of the symmetry, and maybe you can play with it a bit. And what you're going to see is that the covariance here indeed is about 0, but of course there's a high dependency between the relationship, between the variables x and y. So the covariance, so there are two important messages here. So the first one is uncorrelated does not imply independence. And this is what you always read also in the textbooks. This is something to actually remember. If you have uncorrelated random variables, there is not going to be independence, typically. I mean, if you have independent random variables, they are also being uncorrelated, but this other direction does not work. So this direction is true. However, what I'm heading here at is correlation is just one way of measuring how dependent random variables are. And in machine learning, there are many other ways in which you could measure the dependency between random variables. You could look at Kullback-Leibler divergences, for example, or you could look at mutual information, or there are many different measurements, and we're going to discuss them later in the lecture. And what I want to really convey to you is correlation and covariance essentially look at linear relationships. And if what you're hoping to find is not a linear relationship, then the covariance and correlation is not the tool that you should use to evaluate whether this relationship is there or not. And this is something that's really very important to get. Let me maybe make one more figure, which is on my notes here. Independent random variables. How would that look like? So we have x and we have y. And maybe our measurements look like this. No, that's not a good example. Let's maybe, I was about to draw independent, like a normal distribution. The two-dimensional is of course independent if it's centered, but let me even make something much simpler. We have distributions on the unit sphere, like x is between 1 and 0 and y is between 1 and 0, and we have essentially a uniform distribution here. Now what happens is, if you know x, there is nothing you can say about y because we are independent. This is what I want to show you here. So this is independence. So no matter where you are at x, the distribution in the y direction essentially looks more or less the same. And the other way around also, if I'm here, if I'm at y at a certain point, I cannot predict anything about x. This is really what it means to be independent. Okay, I think we are going to see more of this along the lecture, but this is something that's important to me. Now we're still not done with the lecture on variance and covariance because I still want to list what are some of the important properties of variance and covariance. Properties. So what do we have? So these are essentially a bunch of helpful formulas, if you like. The variance of x is, you know the definition hopefully by now. You can also write it in e of x squared minus the expectation of x squared. So once you have the square inside and once you have it outside. You can write the covariance of x and y as being the expectation of x times y minus e of x times e of y. Observe, if we have independence, then we already know that the expectation factorizes, so then we have obviously 0. But if they're not independent, we will get a number that is not 0, typically. Well, not all. Well, sometimes we still get a number that is 0, but we don't necessarily have to. So then, linearity of the expectation I already covered, but maybe let me write it down once more. Expectation of a times x plus b is the same as a times expectation of x plus b. What else? For the variance, we have a slightly different looking formula. Variance of a times x plus b is a square the variance of x. And so you need to be a bit careful here. The square is because we're looking at the power of 2 here, and the b disappears because this is just the offset that would occur both in e of x and x, so the b doesn't doesn't make it into the right-hand side. What else do we have? We have that covariance of x and y is the same as the covariance of yx. So this is a symmetric function. That's also, I mean, that's obvious from the definition. There are deviation measures which are not symmetric. Something like the Kullback-Leibler divergence that is often used in machine learning. This is not a symmetric function. What else? The variance of x plus y is, I write it down, the variance of x plus the variance of y plus the covariance of x and y. And here you see again, if x and y are independent, the covariance is 0, and then we get again the positive, like the fact that we can take the sum of of independent random variables, and the variance splits in the, well, sorry, this was not a good way of saying it. Start again. So if the covariance is 0, then the variance of a sum is the same as the sum of the variances. And this we could also see from this formula, and here we now have an expression that also works for the more general case and tells us essentially what is this offset term that we need to add to take into account that we don't have independence here maybe. What else do we have? I have on my list something I've already said quite often. So if x and y are independent, then the covariance of x and y is 0. And we don't have this direction, we have already had that. And in particular, I mean, maybe I just write it down once more, the variance if x and y are independent. If x and y are independent, then the variance of x plus y, this is just what we said, is the variance of x plus the variance of y. Okay. I mean, there are millions more formulas out there that you could use, but I think these are sort of the most basic ones that you would need, and everything else you can look up. So in the assignments, we are going to have quite some assignments where you need to manipulate all these objects, compute expectations, variances, and deal with dependency and independency between random variables and covariance and so on. And I hope for machine learning and data analysis, it is really, really, really important that you get a good intuition what these notions are, and get a good feeling for what does it mean if random variables are correlated or uncorrelated and so on.